Hey everyone, and welcome back to our flipped chemistry classroom, easy for me to say. And today we're talking about stoichiometry. So we've been building towards this. We've learned how to convert from atoms to moles, from mass to moles, and now from atoms to moles to mass. And we've also learned to convert from moles to volume. So we've been circling around this idea of the mole, and now we get to jump into the meat of this unit, which is stoichiometry. And we're still building towards that project of making the best fireworks. So you guys said at the outset that we need to know the ratio of the chemicals in order to make the best fireworks. And so what stoichiometry is going to allow us to do is to determine those ratios and to figure out how much of each of the chemicals we need to get the best reaction. So let's jump right in. First, by defining stoichiometry. So stoichiometry is just the study of the quantities of materials that are consumed in reactions and produced in reactions. So it comes from the Greek words stoichion and metros, meaning measuring elements. And so when we do stoichiometry, a lot of the time we want to kind of reason backwards. So according to Sherlock Holmes, in solving a problem, the grand thing is to be able to reason backwards, a useful accomplishment and a very easy one, but people do not practice it much. And so in chemistry class, sometimes we do practice reasoning backwards. And so you'll remember that we talked about our problem solving steps. We want to identify our given, that's our G. We want to identify the unknown. So that's where we're working backwards. So the unknown is the end of our project or our problem, and we want to work backwards from the unknown. E, we're going to determine what equations or conversion factors we're going to need. We're going to solve our problem, and we're going to check our significant figures. So quick review of our chemical equations, because now we are not just converting within one element or molecule, but we're actually going to be figuring out how many of each reactant and each product we have and can make. And so we have to come back to chemical equations. And so we recognize that a chemical process or a chemical change is one where we reorganize the atoms in one or more substances. So in this case, we're starting with ethanol, we're reacting it with oxygen, and we're getting carbon dioxide and water. And we call all the things we start with, the compounds we start with, reactants, and the other side, products. So we balance our equation in order to obey the law of conservation of mass. And we have quantitative significance to that balanced equation. So the fact that we have this understood 1 in front of ethanol and the 3 in front of oxygen means that we have 1 mole of ethanol reacting with 3 moles of oxygen to produce 2 moles of carbon dioxide and 3 moles of water. And since we know that moles are proportional to mass and to volume and to number of atoms, we can figure out how many of any of those things we might need for the reaction or how much we might produce with this reaction. And one of the key things in that calculation is this thing called a mole ratio. And so the mole ratio is just one more conversion factor. And this conversion factor relates the number of moles of any 2 substances involved in a chemical equation. And we need that because we want to be able to determine the number of moles of a product or a reactant in a reaction, given the number of moles of anything else in that reaction. So if we were to go back to our previous example here, our chemical change, here we know that we have 3 moles of oxygen for every 2 moles of carbon dioxide, or 3 moles of oxygen for every 3 moles of water, or 3 moles of oxygen for every 1 mole of ethanol. And so we have those mole ratios, and we're going to be able to use those as conversion factors in stoichiometry. So in order to find mole ratio, first thing we're going to do is balance our equation, and we're going to determine those mole ratios, and then we can use those mole ratios to work from our given to the moles of unknown, whether that is a product or a reactant. All right, so if we want to calculate masses, we are going to convert, and this is our typical stoichiometry problems. We would be given an amount in mass or volume. We're going to convert that to moles. We're going to use mole ratios to calculate the moles of the substance we're being asked about. And then we're going to convert those moles to mass or volume if necessary. And let's walk through a problem, because I think this always makes a lot more sense when we have a problem beside us. So here's our question. 6.5 grams of aluminum react with an excess of oxygen. How many grams of aluminum oxide are formed? So first step is always going to be to write our balanced chemical equation. So our reactants are aluminum and oxygen. So we have aluminum and oxygen. There we go, reactants, aluminum and oxygen. Okay, and it asks how many grams of aluminum oxide are formed. So we're going to write our products. Now, as always, when we're writing an equation, we want to make sure that we've written aluminum, oxygen, remembering that oxygen is diatomic. So when oxygen's by itself, it needs a subscript 2. And then that our ionic compound is neutral. So aluminum has a +3 charge, oxygen has a -2 charge. So the formula for the compound is Al2O3. And then we need to balance that chemical equation. So we see this 3 on oxygen and 2 on oxygen. So we're going to put a 3 in front of the oxygen, a 2 in front of the aluminum oxide, and that's going to require us to put a 4 in front of the aluminum. So now we've balanced our equation. We've completed step 1. But we want to figure out how many grams of aluminum oxide are formed. So we've balanced our chemical equation. Now we need to start with the given, 6.5 grams. We're going to convert that from grams to moles, because we want to get to grams of aluminum oxide. I don't know the conversion between grams of aluminum and grams of aluminum oxide, but I do know how many moles of aluminum I have for every mole of aluminum oxide. So first conversion is going to be from grams of aluminum to moles of aluminum. I'm going to look up the mass, the molar mass of aluminum on the periodic table, put the molar mass in grams on the bottom, 1 mole on the top, so that I can cross out grams. And now we're going to convert from moles of aluminum to moles of aluminum oxide. So we have 4 moles of aluminum for every 2 moles of aluminum oxide. So now the moles of aluminum are going to cross out, and I have moles of aluminum oxide. And one last step, I need to convert from moles of aluminum oxide to grams of aluminum oxide. So I'm going to look it up on the periodic table. I'm going to add up the masses of 2 aluminums and 3 oxygens, and I'm going to get that for every 1 mole of aluminum oxide, there are 101.96 grams of aluminum oxide. Moles of aluminum oxide cancel out, and what I'm going to be left with is grams. My answer should have 3 significant figures, and we have 12.3 grams of aluminum oxide. So hopefully that's helpful. We'll walk through this process in class tomorrow, but make sure that you understand that we want to start by identifying the given, the 6.5 grams of aluminum. The unknown, well, first we start by balancing a chemical equation, then identifying the given, then identify the unknown, then convert the given into moles. Then we use the mole ratio to convert to moles of unknown, and then we use molar mass to convert from moles to grams, because that's what we were asked to find. I hope this is helpful. As always, if you have any questions, let me know, and I'll see you in class.